we go, ladies and gentlemen. Strap yourselves in. We're going on a trip of auroras. Somebody please tell me in chat that you can see this okay. Yes, okay, great. Here we go. Well, let's start with some historical highlights about what people used to think about auroras, or what we now call auroras. They didn't know what to call them. If you can imagine way back in time, here we go. There have been all kinds of interesting poetic descriptions to describe these dancing lights in the sky. There's really nothing else you can call them. As long ago as 30,000 BC, this cave painting that you see here in southern France, what's called the Macaroni cave painting, is thought to depict an aurora. But the first really ironclad evidence we have was from 2600 BC in ancient Chinese folklore, that someone saw strong lightning moving around the sky. And, described strong auroras as burning like sulfur and in the shape of a ship, and fire running down pillars like drops of blood. Wow, that must have been a really powerful aurora. In mythology, Eos was the Roman god of dawn, and she rode her chariot across the sky during the day. Her son, Boreas, which was the god of the wind, is said to have made the light move across the sky by the wind. And so that was one explanation. But the Scandinavians have it really down pat. They have all kinds of colorful descriptions. The Finns think that it's the fur from the Arctic fox as it runs along the snowbanks, giving off sparks. The Sami, which are the indigenous people of Scandinavia, northern Scandinavia, had a word for this called guavsashas, which was the light you can hear. And we'll get to this in a little bit about the actually being able to hear an aurora. The Scots, of course, not to be left out, imagine that these were battles taking place in the sky. And some Inuits thought that they were spirits playing ball games with the skull of a walrus. Great terms. Great imaginations that these peoples had, because they didn't know until fairly recently what was really causing it. You can see there some of the colorful names, like glowing snakes and flying dragons. And so it wasn't until none other than Galileo in 1619 coined the term aurora borealis, meaning Latin for northern dawn. And it fell to Captain James Cook, as he traveled around the southern hemisphere, came up with aurora australis, its counterpart. And auroras do happen in both hemispheres around the poles. We'll get to that in a minute. So the first stabs at scientific explanation came from Edmund Halley of Halley's Comet fame, who imagined that auroras were sort of magnetically driven vapors that were rising from the poles of the Earth. And but one of his contemporaries, Jean-Jacques Dartout de Morane, suggested that the aurora is solar matter descending into the atmosphere. Now, this was almost entirely correct, though he didn't realize it at the time. But others poo-pooed it, saying that the sun's atmosphere can't extend so far. Well, we now know that it can. And so more back and forth went between these scientists, that the auroras were more common in the 18th century. They occur constantly in the Arctic regions, which is pretty true. This is from a Norwegian. He should know. And yet there was still this sort of notion that it can't be external. It's just lights being reflected off the snow. Well, not until the early 20th century, in particular, Christian Birkeland did experiments in a laboratory using a box with a lot of the air sucked out of it, a partial vacuum, and he fired electrons at a magnetized sphere. And that sphere turned out to have glowing ovals at the north and south poles of its magnetization. And so this was the first hint as to what is really going on. And so I can tell you that an aurora is like a fluorescent light bulb. That's really all that's going on. So if you imagine what's going on inside a fluorescent tube, the electrodes at the end are sending a stream of electrons through the mercury vapor that's inside the tube. And when one of those atoms of mercury gets hit by an electron, it becomes excited. And in order to get unexcited, it has to give off energy. It does so in the form of ultraviolet light. Now, we can't see ultraviolet light with our eyes, but there's a coating on the inside of the tube called a phosphor that absorbs the ultraviolet light and then re-radiates it as white light that we can see. So that, in essence, is what an aurora is. It's an electromagnetic phenomenon. The source of the aurora, at least the source of the triggering mechanisms for the aurora, are found in the sun. This is a picture of the sun as it looked today. NASA has a number of satellites that are constantly monitoring the sun. This is the Solar Dynamics Observatory in particular. And this is the sun. You can see it's got a number of black spots on it. These are called sunspots. And this is how it would look to your eye through a filter, maybe one of the filters you've got left over from the eclipse. If you went out, you could see the sun this way. But if you could look at the sun with X-ray vision, it would look like this. It's a very wild and turbulent place. All of those swirls and loops and stuff that you see, including off the edge there on the left and right, are showing us matter on the sun, which is highly, very hot. It's been reduced to, its electrons and protons. It's what's called a plasma. And that plasma is being controlled by loops of magnetic field that are looping up from the sun's surface. And so all of this starts deep, deep down in the sun, inside the sun. The sun is very highly magnetic. In the core is where the fusion happens that converts hydrogen to helium. So that is the source of the sun's heat and light. But it takes a lot of time for that energy to work its way out from the middle of the sun out to the outside edge, what we call the photosphere. And in the last part of this process, in what's called the convective zone, sort of the outer quarter of the sun, that energy is being passed off by churning matter. Think boiling oatmeal, and you have a sense of what the convective zone is all about. And it's within this convective zone that the sun's powerful magnetic field arises. So this is a little movie that I put together from the last 4 days of the sun, and you might be surprised to realize that the sun spins. In fact, it does spin. It spins about every 4 weeks. And unlike the Earth, where everything is rotating all at the same rate, the sun has what's called differential rotation. It's essentially an enormous ball of fluid, about 1 million miles across. All of the sunspots you see there on the surface are at least as large as the Earth, maybe bigger. And it turns out that the sun spins faster around its midsection than it does at the poles. The equator takes about 25 days to go around. The poles take 33. And this differential rotation, what it's called, causes the magnetic field lines in the sun to get wound up like a watch spring. And when those magnetic field lines get wound up, there's a tension, there's potential energy stored in these extended magnetic field lines. And when those field lines have the opportunity to touch one another and short circuit, think of a rubber band that's stretched out and then you snap one end into the other, you get a release of energy. And it's not like releasing a rubber band. This is titanic amounts of energy being released on the sun. Not only is matter thrown out into space, but also you get these enormous bursts of energy, as you'll see here in this video. This is what's called an X-ray flare. This one is from a few years ago. And these X-ray flares release lots of X-rays, obviously, that's why they call them that, and also relativistic particles, protons and electrons, accelerated to nearly the speed of light and flung toward the Earth. And so this is very dangerous for satellites, as you might imagine. You don't want these flares to get too intense or it could do damage. But in addition to that, these flares also eject huge amounts of matter out into space. And this is an example of one of those eruptions. You see that it's not just a bubble, it's actually got structure. And all of the structure that you see there is because of the magnetic field lines that are threading through all of this very hot matter. And so when that matter gets ejected out into space, it creates a kind of shock wave that heads toward the Earth. Now, we have many satellites in orbit now that help us predict when there are going to be eruptions of the sun. Let me explain. The white circle there that you see at the center represents the sun. That's how big the sun is. We're looking toward the sun with the spacecraft. The black circle is a mask that is blocking the sun itself so that it's not blinding. All the orange and yellow that you see around the outside is matter escaping from the sun. This matter is escaping all the time. We call it the solar wind. The sun is constantly losing mass as it flows away from the sun out into interplanetary space. But when these eruptions take place, you get an impulse of a lot of matter being ejected all at one time. So watch what happens here on the right-hand side. Bang. That's called a coronal mass ejection. It's a mass CME. It's a lot of matter being thrust out from the sun at very high speeds, 500, 600, 700 miles per second out into space. Now, in this particular case, you can see that it's off to one side. So this particular CME would not have been a problem for planet Earth. But now take a look at this one, this next one by comparison. In this case, you're going to see that the eruption is all around the edge. It's not just in one spot, it's all around, kind of like a blooming flower. And when astronomers see that, they know that this CME is headed toward the Earth. It's literally a shock wave of matter heading toward the Earth. Now, this mass can also escape from quiet patches where there is no magnetic tangle. We call these coronal holes. So all of these different locales on the sun's surface can create ejections of matter that end up attacking the Earth and creating an aurora. This is what a little animation showing coronal holes. There's a particularly big one there, right there. And so what happens to that matter after it's ejected from the sun is that it spreads out into interplanetary space, eventually connecting with the Earth, impacting the Earth and its magnetic bubble. So this is a little animation with a gentleman with a nice English accent, so he must really know what he's talking about. Listen up.
During solar maximum, solar storms can occur several times per day, and sometimes they are aimed in the Earth's direction. When the solar storm reaches Earth, something strange happens.
Oh, sorry.
It's as if it is deflected by an invisible shield.
Pay close attention to the direction of these magnetic field lines.
The magnetic fields couple together and create a funnel for the gas streams down on the daylight side of the pole. This is the daytime aurora, which our eyes cannot see. The magnetic fields stretch further rearwards and couple together. The magnetic fields stretch like a rubber band, and gas from the solar storm streams back along the magnetic lines towards the polar regions on the night side. This is nighttime aurora you can see.
Right. And so just to be clear here, there are different, Earth has 3 different poles. The geographic pole is where the spin axis comes out. But our magnetic pole and our geomagnetic pole, which are not in the same location, are what affects the intensity of the auroras. And it's actually the geomagnetic pole, the one that you see there just off the coast of Greenland right here, that is the center of this oval of cascading electrons that are coming in from the tail of our magnetosphere. And, you know, when that solar blast wave hits the Earth, the Earth's cocoon, its magnetic cocoon called the magnetosphere, protects us largely, but sometimes they couple together in a way that allows this matter to stream down into our polar regions, and that is what's causing the aurora. So this is from a spacecraft that was some years ago, but it shows you quite dramatically this oval around the pole. So here's Asia down here. This is North America. We're looking down the pole. Here's Greenland, and you can see this oval. These ovals occur in the northern hemisphere and also the southern hemisphere. So here's Antarctica, for example. This is taken at the same time. There's an oval around the South Pole and an oval around the North Pole also. And so what these auroras look like, this is taken by astronauts aboard the space station. They are, I need you to think of this as Earth under attack. These are electrons streaming down from a great altitude. They are attacking our atmosphere. Now, this takes place very high up. We don't have anything to worry about here at the ground level, but it's causing the gases in our atmosphere to glow in a very distinct way. And so these auroras have very distinct colors. Typically, green and red are the most common, with the red on top. And I'll get into why that is in just a second. But importantly, it wasn't realized until the fairly late in the 1800s that auroras were not continuous emissions like the sun puts out, but very specific lines. Think back to that fluorescent bulb for a second that I told you about. The aurora is only emitting light at very specific wavelengths of red and green and sometimes blue. And here's a funny little video clip trying to explain kind of what's going on.
Well, what else have we got which has got something peculiar about it? This one here has got a siren, which I've had for many years.
Okay, good.
That is noisy. I need it once. And a smaller one. Yes, kids love them.
Okay, good. I'm sorry about that. I'm glad we got that sorted out. So I'm going to teach you, let's see. I'm going to teach you everything you need to know about atomic excitation with this balloon. Now, imagine this as an atom in its rest state. There's no forces on this balloon. It's sitting there limp. It's very happy to stay limp like that. But when I blow into it, I'm changing its character. Think of this as an atom in its ground state. And when I do this, I've excited this balloon. This balloon now I've transferred energy to this balloon, and it doesn't like being this way. Balloons don't like being inflated. So to get rid of the energy, it does this, right? And that sound, that escaping air, is the energy from that excited balloon, if you will, being released. Auroras act the same way. They are atoms of gas high in our atmosphere that are being hit by electrons from the solar wind, and they become excited. And then when the atoms are excited, they give off a photon of light at a very specific color according to their composition, and that's what causes the aurora. So, for example, in the uppermost atmosphere, way above 120 miles, the gases that we have down here at ground level, carbon dioxide and water vapor and things like that, do not exist very high in the atmosphere. By the time you get high up, you're down to like very little amounts of oxygen and nitrogen, often as individual atoms, not as molecules. And so it is there when these electrons hit oxygen atoms, very thin atmosphere, hardly anything left. We're practically at orbital altitudes at this point. It causes them to glow red. They give off a red photon to get rid of this energy. A little bit farther down, we have nitrogen molecules that are giving off a blue light. Farther down, again, oxygen, but this time the oxygen atom has been ionized. It's lost an electron. And when that gets excited, it gives off a green photon. And then finally, down at the bottom, we have, let's see, I guess there is a fourth one there. I'm not sure what happened to it. I'm sorry. In any case, the two distinct colors that you have for auroras almost all the time are red and green, both caused by electrons interacting with oxygen. Atoms of oxygen higher up and ions of oxygen lower down for the green. Now, here's the thing. Your eyes don't see color well at night at all. Our eyes have two kinds of sensors, rods and cones, and during daylight, our cones are red, green, and blue sensitivity in the eye respond to light and show us color. They show us the world in color. But at night, that light is not bright enough. You see the sensitivity, it's much lower than the rods, which is our nighttime vision. It's what you think of as your night vision. Rods are 1,000 times more sensitive than cones to light. So we can see actually pretty well at night, but the rods are a black and white system. And so at night, when you're walking around, you really only see color when that source of light is bright enough to trigger your cones into seeing a color response. And so this is an actual photograph of an aurora, and you can see the beautiful reds and violets and greens. But to our eye, that same aurora would seem basically as shades of gray. And so here in Massachusetts, we will sometimes hear, as we have today, that there's a chance of seeing auroras. And in that case, what you want to do is look toward the northern horizon, find a clear spot away from city lights if you can, and don't look for color because you're unlikely to be seeing color like you see there on the left. Instead, look for weird shaped clouds that maybe have a lot of vertical structure to them that seem to be moving around in weird ways. Then that could be the aurora. Could be the aurora. Okay. So jumping forward, there are different kinds of auroral shapes. The most common ones that we see are these curtains of light that are like very wide, gently curving bands. There are rays, which are a little bit more impulsive. They're like daggers of electrons jutting down into the atmosphere. These are the ones that I think are most telling in that Earth is under attack, these rays, and they can come in all kinds of shapes and forms, but they're very strongly vertical in shape. And then if you ever happen to be lucky enough to see an aurora converge directly over your head, all of these shapes combine to form a kind of perspective effect called a corona or crown. And it's a violent dancing set of clouds. This is one that was taken in Iceland a couple of years ago. This is actually taken with a smartphone. This is one taken just a couple of months ago in Minnesota by a friend of mine, one of my colleagues at Sky and Telescope. They are very, very dramatic. And then on the other end of the spectrum, sometimes you just see these sort of vague bands. And that's often what we see here from New England. We don't really see a lot of structure in the auroras. We just get a sense of undulating clouds. Now, there are a couple of atmospheric phenomena caused by electric fields, not unlike an aurora, that are not caused by the sun. Here is one of them. This is just for completeness' sake. It sure looks like an aurora, but it technically isn't one. Now, early on, I talked about how the Sami imagined auroras as the light you can hear. And there have been many, many reports over time, historically, of auroras that were strong enough to create a kind of hissing or crackling sound in the background in the otherwise quiet night. And these have been, they were sometimes dismissed as being just, you were just imagining that, but they have persisted. And so very recently, within the last 10 years or so, scientists have figured out exactly what's going on. Now, remember, the auroras are happening far, far up in the atmosphere, 50, 60, 70 miles up. So it's inconceivable that it could be a sound wave generated that high up and making its way to the ground. It has to be something else. And so this rather complicated looking set of graphs involves, on the top, the dark blue line is radio energy being recorded during an aurora. And then the red line is actual sound, a sound recording. And the offset of the two of them, of those two curves, suggested that whatever was creating the sound had to be very close to the ground, about 250 feet up. And this is what scientists think are happening. When you have particles in the atmosphere, like haze, smog, smoke particles, and especially in Scandinavia, a lot of those people, especially in rural areas, burn wood and such to get their homes warm. So you have a lot of particulates in the atmosphere. It's possible for the aurora to create a static charge in an inversion layer of those particles. And when the charge snaps, when that spark happens, that is what's creating that static discharge is what's creating the sound. So it does seem to be real. And in fact, the Finns have established a listening post that will both record the auroras and record the sound at the same time to extend this research. I want to just mention briefly that auroras are not just on the Earth. We know that there are auroras on Mars. They are at ultraviolet wavelengths. This is a map of Mars showing where auroras have been detected. We know there are auroras around Jupiter. Those happen to be ultraviolet also, and around Saturn, they happen to be infrared. None of these we could see by eye. We have even got a sense that auroras are happening on other stars and the planets of other stars. So it's a widespread phenomenon. The chance of seeing an aurora, well, that's what we're going to tackle next. The sun has an activity cycle, long-standing activity cycle. It's been known for a couple of centuries, lasting 11 years. The sun gets very active, then it gets very quiet. Gets very active and very quiet. This is in a magnetic sense, the number of sunspots, for example, on its surface. And this 11-year cycle, we're now in the 25th recorded activity cycle for the sun, solar cycle 25 it's called. And early on, a year and a half or so ago, solar scientists got together and they predicted how strong this solar cycle would be, and that's the red line. And what happened was, and by the way, it was not expected to be a particularly strong solar cycle. Not a lot of sunspots, not a lot of auroras. But what the real observational data are the black spots and the curved purple line that you see there. And this solar cycle came on stronger and faster than anyone expected. And so they've now had to revise their prediction. And the prediction is that the peak of this solar cycle, 25, is going to happen within the next 6 months. And you can see that it's still much stronger than had been anticipated by the best minds in the business. So if you want to know when an aurora is going to happen, where this is all taking place, let me send you to a great website called the Space Weather Prediction Center, swpc.noaa.gov. This is a very user-friendly dashboard where you can find out all kinds of information about the state of the solar activity, the state of storms. And on this website, you're going to see, this is what you want to key in. There are two numbers that will tell you, like a pro, whether there's going to be an aurora tonight. And this is what I've been watching all day. The first of these numbers is called the KP index, which is a measure of how much Earth's magnetic field is being disturbed by the solar wind. It goes from 0 to 9. 9 is the top number. And once we get about 5 or 6, then that's when we start hearing these alerts that maybe auroras are in our future. The other number, so this scale goes from 0 to 9, and it corresponds to the degree of the geomagnetic storm that results from 1 to 5. I'm sorry, there's two confusing scales there, but basically this KP index is what everybody watches to find out how strong an aurora might be. The other number that's really important is the orientation of the sun's magnetic field. You remember that the video that didn't have any sound, again, I'm sorry for that. I mentioned to watch the polarity of the magnetic field. When the sun is sending a shock wave, a coronal mass ejection our way, if its magnetic field has the same orientation as the Earth's magnetic field, they're going to repel each other. No aurora will happen. But if the fields are opposite like this, they can couple. And so when this B sub Z, that is the direction of the auroras, the solar wind's magnetic field, becomes negative, that is a clue that an aurora could happen. So here's an example. I want you to pay attention to this red line right here. If it's negative, an aurora can happen. If it's positive, it can't happen. And so I went just before this presentation, I went and I grabbed the latest forecast so I could show you what's going on. You can see that this is for beginning September 13th, but this is in what's called universal time, which is the time in Greenwich, England. This is for the period right now, from 8 p.m. to 11 p.m. right now. You can see that the KP index is pretty high. It's at 6. 6, if you were following, that's strong enough to be triggering an auroral display. So that's good. You can see that basically all night tonight, what great timing, right? All night tonight, there is the potential for auroras. But the other thing, or let me just explain what's going on here, that when those indexes get high, the higher those indexes, the farther south those auroras go. So these are curves showing North America, and here in New England, we might expect auroras about 5 times a year, and those will be occasions when the KP index gets around 6 or 7. So I said that it's predicted to be 6 right now. That's good enough for maybe after we're done here is for you to go out and find a nice clear spot somewhere and look toward the north for a possible aurora storm. As I mentioned, they happen in the southern hemisphere as well. And it's also the case that at certain times of year around the equinoxes, that is in late March and late September, there's a slightly better probability of an aurora taking place, which is right now. So we've got everything working in our favor tonight, right now, except for the fact that the moon is kind of bright. But, we have a strong geomagnetic storm going on. And let's see, I think I grabbed, well, in a second, I'll show you the magnetic properties. This preference for the around the equinoxes has to do with the fact that the Earth's spin axis is tilted, and it's at this time of the year, if you can think about it, that we're not tipped toward the sun or away from the sun. We're kind of sideways. Our tip is sideways, and that seems to make it much more active aurora-wise. Now, some of you remember that back in early May, there was a titanic aurora storm where the KP indexes would literally hit 9 for the first time in 20 years. And there were auroras all over the place, including around here. This is what it looked like. This is a depiction of the extent of the auroras. We saw auroras down here in Massachusetts. I saw them. Maybe many of you saw them as well. I don't think we're going to be there tonight, but this shows you the KP indexes that were present during that period of time on May 10th and 11th. This is super strong stuff. It's topping out the chart. So it was a great time to be looking for auroras. And in fact, a friend of mine, these are a couple of aurora pictures taken from Cape Ann and southern Maine. There's a corona there on the right. It was quite a dramatic thing. So you don't need to take my word for it. If you don't want to go to the Space Weather Prediction Center and sort out the charts and graphs, I wouldn't blame you. Here are a few apps that you can download for your phone. They all use that space weather data as the basis for the predictions that they present, but it's a little bit more of a user-friendly vehicle. I'll leave that up for a second. Auroras, we're right in the middle of the solar maximum. So auroras are going to happen, and they're likely going to happen and be visible from around here in Massachusetts and at similar latitudes all across the country. Okay, I want to tell you a story before I close. Sky and Telescope does a number of astronomically themed tours, and every year we send a tour group to Iceland for the purpose of trying to see auroras. And this was the group that I led in 2019. That's my wife there in the striped sweater right in the middle. We have fantastic time. If you ever get a chance to go to Ireland, go. It's an amazing place. So many amazing waterfalls like the one you see behind us there. Well, we were there to see auroras, and the sun was not cooperating. We were at solar minimum. You can see there is not a single spot on the sun on the day we arrived. In fact, we got there a day early, and we were waiting for the rest of the group to show up. My wife and I encountered a group of astronomers from China who had been in Iceland for 2 weeks to look for auroras. They had seen nothing in 2 weeks. This did not bode well. But what I had going for me, my hope against hope, was that there had been a big coronal hole facing directly toward the Earth on the day before we arrived. And maybe, just maybe, enough of a pulse of solar wind escaped through that coronal hole to impact the Earth and give us coronas. So everyone showed up, we went to our hotel, and this is what we saw the first night we were there. And this is more of that. It was an amazing aurora display that just completely blew us away. We had no real expectation of seeing this. It was really fantastic. I made a little time-lapse video that you're going to see here of the aurora dancing across the sky. Here's the Big Dipper right here in the background. It was really, really excellent. We saw strong auroras for 3 nights. It was not in the, we had not expected it, and we just lucked out. And this is my take home for you, that auroras can come at any time. And so, you know, keep your cameras handy. Here are I'm going to give you 2 or 3 expert tips for how to record the aurora. The first is that your smartphone is probably good enough. You want to switch it to night mode photography, and that's makes it more sensitive to the colors. And you know, if you're ever in a situation where you're not sure by eye whether you're seeing an aurora or not, take a quick snapshot with your phone. You'll see the color of the aurora shown in the image, and if it's green, yes, you're really seeing an aurora. The second thing is, you might think this is obvious, but turn the flash off. It's not going to do you any good. And it just messes, it confuses the camera when the flash is on. It thinks it's supposed to be taking a picture of something close in, and when it's really not. And then finally, if you can, hold your phone as steady as you can. Brace yourself against a wall or a tree or something, somebody else on their back, whatever, to try to keep the camera steady while you take the shot. As I mentioned, this photo was taken on one of our tours with a smartphone, so it can be done. I'm going to skip over this because it's a little bit higher order than I think I need here tonight. But what I'm going to close with is a video of auroras from Iceland, set to some music that I hope you'll enjoy. Auroras from a few years ago in Iceland. So very beautiful. It truly is nature's light show. And so I've unshared here. And what I'm going to do is I'm actually going to start with the Q&A section. There's only 5 questions here, and then I'll jump over to the chat and see what's in the chat. So Anne says, can you explain how we take images of the sun's activity? It's being monitored constantly, Anne, by a whole series of satellites launched into space specifically for that purpose. You can imagine that these solar storms can be very disruptive. They can disable satellites, they can affect our power grid, and so we want a little advance warning that they are coming. And Teresa wants to know what happens to folks who are colorblind. Well, Teresa, happily, you can still see auroras. And you just can't see the colors as well. And, you know, since they are primarily gray to our eye, for example, those displays that I showed you from our first night in Iceland, I was not seeing color. I saw the clouds all dancing around, but it was just shades of gray for me. And so you also ask whether these can be translated into sonifications. If you mean taking the wavelengths of the emissions and converting them in some sort of transform into sound, I've never heard that done. I suspect it would be possible to do. And just a final wrap up, that website to go to is, first of all, you can just Google space weather. That would be enough. But it's the Space Weather Prediction Center, SWPC. .noaa, NOAA.gov. NOAA stands for National Oceanic and Atmospheric Administration. It's the government weather agency. So swpc.noaa.gov is where you will go to get all the information there. And yes, anonymous attendees, some of the apps that I showed you are free. Not all of them are. I didn't pay attention to which ones cost, but you know, apps are very inexpensive. They're just a few dollars. And maybe it's the same person. Yes, Sky and Telescope definitely tries to hold its trips when the auroras are predicted. We tend to do them in late fall, around the time of the equinox. And obviously, we want to go there when the moon is not in the sky. And so, Thomas, to your point, they are slightly seasonal. They do tend to be more pronounced at the around the equinoxes in late March and in late September, early October. Now I'm going to jump over to the chat for just a couple of minutes and see if there is something here. Francine asks some time ago, why did I say that it's dangerous to Earth? Well, when you have all of these electrons cascading down through our atmosphere, most of them are repelled by the magnetic field, but the ones that get through interact with the gases very high up and give us the auroras. Those are completely harmless. If you happen to be a satellite higher up than the auroras are happening, then you can be struck by these energetic electrons and protons and, you know, get short circuits and cause your function, electronic function, to be degraded. In addition, let me tell you this about the most powerful geomagnetic storm ever recorded was in 1859. It's called the Carrington event. And back then, the internet was telegraph. That was how we communicated with one another along, if you can imagine telegraph wires, very long strands of wire stretched across the prairies and plains and such. And when these auroras happen, they induce electric fields in the ground and especially in conductors like a telegraph wire. The Carrington event was so powerful that it caused the keypads, the telegraph operators' keypads at the stations, to smoke, and I'm told even to burst into flame. So if you can imagine how sensitive our modern day electronic infrastructure is, I think we are actually quite susceptible to a lot of damage from a very powerful geomagnetic storm. And actually, companies like the power grids and so forth have taken steps to make their systems kind of resilient to just this kind of auroral geomagnetic activity. Okay, tell us again why, JM wants to know why it was mostly green in the auroras in Iceland. Believe it or not, JM, it's because it was, as much as it was active to us, it was actually a fairly weak storm. And the weakest storms predominantly are going to be green. That's what I would expect to see most often here around Massachusetts is greens. The reds, which are higher up, are pretty obvious. Our eyes are not particularly sensitive to red light at night, even less so than green. That's where your cameras will come into play, where that can show you the greens and the reds where the eye cannot. I want to thank you, all of you, for coming. Enjoy the lunar eclipse coming up. Head outside and see if there's some auroras. Dash over to the Space Weather Prediction Center and see if there's an aurora in the offing for us. I sure hope so, and I hope you get to see one in the very near future. I don't know where my handler is, but I guess I'm going to just end the recording now. Thanks again, and we'll see you soon. Bye-bye.